First of all, I would like to congratulate the organizer, first of all, for a fantastic tutorial. As was said before, there should be more tutorials like this at ICRA, I think. And also thank them a lot to being invited, because I was at the tutorial as an audience last time. I enjoyed it very, very much. So I want to start very quickly by making some comments of certain things that came up during questions and stuff like that. So first of all, about manifolds in general, please do realize that manifolds in general have no shape. So, and then they have no structure and no shape in general. Differentiable manifold is actually what we've been using so far in the tutorial, in which you have a differentiable structure to do. But it's a structure, it's something you add on the manifolds, okay? If you also add an extra structure, which has also been added here so far, is the Riemann structure, then it gives shape, okay? So a manifold without a Riemann structure does not have shape, because in general a manifold is something abstract. You don't need to embed it in another space, but as we've done so far. And describe the distance. And dynamics is, for example, a typical example of how you use a Riemannian manifold to talk about dynamics. Lie groups is about symmetries, it's a different thing, okay? And a Lie group acts on manifolds to find symmetries, okay? Example of Lie groups are SO3, for example, and SO3 and quaternions, which are equivalent, is actually a Clifford algebra, which is actually isomorphic to SO2, which is a Lie group, and quaternions and rotations are not equivalent. There is something very deep that couple these two, called double covering, and has to do with quantum mechanics and other things as well, but are not the same. And about metric, a Lie group only has a metric if it's semi-simple. So only certain Lie groups have an intrinsic metric, okay? And if semi-simple, for example, SO3 is semi-simple, but SE3 is not semi-simple, okay? And in fact, as no intrinsic metric, and this was a problem in the 90s, to talk about hybrid position force control, people were saying, what's going on here? And this was actually because they didn't know this geometry. And parallel transport in Lie groups, okay, is intrinsically independent of any, in some sense, it's not called parallel transport, but is really intrinsically built in the symmetries that the Lie group represents, and it's independent on the trajectory you follow, because in the Riemann manifold, it does represent on the trajectory. And if you have a certain topology, using geodesic, you can have a geodesic on one side and geodesic on the other side would give you a different result. So you need to be a bit careful. So there are a lot of issues in this stuff that needs attention. And accelerations, as we used all the time, are probably not defined in the way that most of the people use it. So this tutorial is very, very valuable, because there is far too little attention to these things in our community. Okay, the motivation of my talk now. So robots are physical systems. Energy is the mathematical embodiment of the invariance of physical laws. Really seriously, historically it's been different, but this is what it is. I'll come to that later. Physical interaction of robots with humans is really one of the bigger things where we have to deal in our community, right? And in many robotic applications, this is very valuable. And yet, very often we don't even look at energy. And this is something that I cannot understand, okay? This really goes behind. So what I want to try to do in this tutorial part is to give you an idea of why you may want to look at port-based way of thinking. And it is what I will tell you during this lecture. So I will first start with an example, a very complicated example, so how to use this geometry for really seriously complicated problems. And then I will introduce some mathematics, and then give you the reason how to model interaction in a proper mathematical setting, okay? And give you a glimpse of control, and then to draw some conclusion. So the example is a project I had the fortune and the pleasure to lead. It was a ERC advanced grants that I got. It's about a robotic bird. And this is a bird we want to study. It's unique in the world. It goes up to 80 kilometers an hour in 5 before wind, and it's really propelled by flapping, and I think it's a unique bird that has these features. And as long as we model the rigid connection between the wings and the body, we know Lie groups, finite dimensional Lie groups and stuff like that. That's easy, but why does that fly? Because it has an interaction between the wing and the flow dynamics that goes around the wings. So when you want to model that, that's nasty, okay? Because fluids are defined, followed, differential equations are called Navier-Stokes, and then elasticity, nonlinear elasticity in a proper geometric settings, without no Euclidean geometry in that respect, so you need to understand the physics of it, is nasty. And you need some other materials, some mathematics that need to be proper, because if I don't see the geometry this is in my mind, I just cannot understand things, okay? So things for me should be coordinate invariant all the time, otherwise my brain shuts off. I want to show you a video about the project for a few minutes, 4 minutes, but I think it's kind of nice.
Nature is amazing, and birds are amazing creatures, but we do not fully understand yet how they can fly. Could we really understand the magic of flapping flight so that we can build robots that can fly better than the robots that are currently available? The Robird is the only robotic bird in the world which can fly in up to 5 Beaufort wind and at a speed of 80 kilometers an hour. It weighs the same as a peregrine falcon, and it looks like it. But do we really understand the underlying physics? We believe that flapping flight is achieved with a combination of flapping and twisting of the wings, which creates detached vortices which generate thrust. But are we at the moment using the optimal combination of the oscillatory pitching and plunging motions of the wing? To answer this question, an experimental setup is built in the wind tunnel of the University of Twente to see how the wing moves and how the stream of air moves around the wing while it's flapping. This allows for exploring the optimal wing motion for the Robird. A helium-filled soap bubble generator is installed, which blows thousands of bubbles per second into the wind tunnel. 4 high-speed cameras film the bubbles to capture the movement of air around the wing with the shedding of vortices. Furthermore, a force sensor at the root of the wing can measure the resulting forces on the wing, like lift and thrust, and reflective markers on the wing can be filmed with cameras to track the wing movement and deformation at a sub-millimeter scale. We have studied the flexibility of the wing since it's an important part of why the Robird flies the way it does. Different than many people think, intelligence can also be embodied in the material and properties. A brain without a proper body is useless for locomotion. We want to bring this physical intelligence in the wings of a robotic bird, and in order to do so, we created smart wing designs and smart mechanisms which are able to change the mechanical stiffness of the wings to change the flying behavior. But how can we precisely describe the physics of a robotic bird with deformable wings interacting with the air around it? The unique feature of the approach we followed to describe dynamical physical systems is that it relies on energy and geometry. Energy is probably the most fundamental concept unifying the various branches of physics and explaining how nature works. In the Portwings project, we used the Port-Hamiltonian framework to get insight into the energetic fundamentals and transport phenomena of fluid dynamics, structural dynamics, and fluid structure interactions. In the Port-Hamiltonian framework, we describe any complex physical system as a network of energetic modules interconnected using power ports that characterize the energy flow within the system or exchanged with the environment. For example, if we consider the flapping wing setup we developed, we describe it as a network that represents the dynamics of the driving mechanism, the elastodynamics of the wing, and the aerodynamics of the air around it. The power supplied from the power source flows to the electric motor, and then some of it is stored as kinetic energy in the mechanism's inertia. Some of it is dissipated as heat and noise, and the rest goes to the flexible wing. The power supplied from the wind tunnel is also transferred to the wing through the moving boundary of the wing and the airflow injected inside the wind tunnel. In each cycle of the wing's flapping, the power supplied to the wing oscillates between kinetic energy and elastic potential energy, while the power that flows to the air is either stored as kinetic energy or dissipated in the vortices formed due to the wing's flapping motion. Our Port-Hamiltonian description of this physical system differs significantly from the standard approach of continuum mechanics using coordinate-based tensor calculus treatments. We rely instead on coordinate-free exterior calculus and describe the network structure of the system using so-called Stokes-Dirac structures. This methodology allows us to intrinsically handle open boundary conditions and thus use, reuse and combine sub-models in such a way that a real Lego of physics would be possible. Consequently, this leads to the development of structure-preserving computational algorithms that allow us to efficiently and robustly simulate these physical systems to produce predictive computer models of the world around us. The real advancements in science and technology are only achieved with a deep understanding of the fundamental theory, as well as proper engineering and experimental skills targeted to the goal to be achieved.
I'm very happy and thankful to the European.
So, if you're interested to see the video, you can also find it on YouTube, so you can download it in 4K if you want to use it. So now let's get to what is behind all this. You can only do certain things if you have right math. There's no escape from that. So I will start from mathematics. And as Poincaré was saying, mathematics is the art of giving the same name to different things. What does that mean? It means to find the real thing, the structure that you need in order to describe things, and to get rid of anything which does not matter. If you want to talk about the dynamic of a rigid body, it doesn't matter what color that has, okay? That's the point. So what is the minimal structure you need? When you want to talk about power transfers and interconnection and modeling, you need to talk about pairing. What is a pairing? Well, you have two sets, and you have a pairing, basically a function that takes n elements of these two sets and returns a real number, in this case. Of course, it can be generalized. Now, if I give you two vector spaces, okay, I take an element from a vector space, an element in another vector space, can I give you a real number? What would be a pairing? Well, we have seen it once so far, right? So this is called an inner product. Fine. But try to be abstract. You know, I'm not using matrices now. We'll get to that later, okay? So it's an inner product, is an extra structure. It's something you did not have before. There is no other way to go from two vectors to a real number without adding an extra structure. There is no way, okay? And this is called a Hilbert space. Well, if it's an infinite dimensional, this still holds as long as the space is complete, what is said, but it still holds. You know, infinite dimensional vector space is just another vector space, which is a bit bigger, okay? That's all it is. And the basis is different things, but the vector space can be finite or infinite dimension. What we've seen so far in the lecture is precisely this. You know, so in each point we have a tangent space. So we take two elements of the tangent space, okay? Then we have Riemannian structure, that's a picture of Riemann, that it basically associates, given the Riemannian structure, a real number, which is taking the inner product of these 2 points. But it's a point-dependent thing. All right. Now, is there a way to do it without adding any other structure? Could we define another set to which we could define a pairing? Yes, it's called a dual space. The dual space is basically the space of linear operator on that vector space, okay? It's very roughly speaking, just for your intuition, don't think that is the thing, but if I give you a vector in numbers as a column vector, right? You can think about this V star as a row vector. You multiply it, you get a real number, okay? But it's not that if you turn it, it becomes another kind of vector. So this is just a numerical representation. This is very misleading, okay? So, but just for your intuition, that's what I'm talking about. If you have this situation, you don't need anything else. You just give me a vector, you give me an element in a dual vector space, is not the same vector space, you get a real number. Have you ever used that? Use it all the time. If velocity is a vector, a force does not belong to the same space, okay? It's a dual vector. And their natural pairing is not an inner product. If you hear that somebody says the inner product between the forces and velocity is wrong, is the natural pairing, it gives you the power that that force attached to that velocity. And this is more related to duality. And duality is, as long as I'm concerned, the most fundamental concept in nature. And so I want to try to talk about in a way that I split the fact that I need a structure, as Hilbert and Riemann would do, to something try to look at a discussion without that structure, which is more related to duality and Poincaré, and to topology, in fact, and not to geometry. And by the way, from a historical perspective, in 1900 there was a big dispute and there was a kind of split in mathematics between what were called the intuitionists, like Poincaré, and the formalists, like Hilbert, Riemann, and other people. So a vector space is different than its dual, are two different spaces, okay? But you can join them. If you take an element one side, an element on the other side, you can join them, and you get a real number, which for us will be power, okay? So now you know that the vector space and dual vector space are two different things, okay? Now a question, do you think you know what matrices are? Of course you say, well, let's wait the end of this. Let's play a game. There are two guys. The one on the right is, oh, this is annoying, this thing. Well, anyway, the one on the right, let me try to see without destroying everything. Where's my mouse? No, forget it then. So there are two mathematicians, Van Neumann, one of the big genius of the previous century, you know, one of the grandfather of the computer, of quantum mechanics, I could spend the whole day to cite what he did. And probably the biggest mathematician of the previous centuries, Hilbert, okay? And Van Neumann was, by the way, a student of Hilbert. And there's a nice story about this. So they are both given a square matrix, okay? But they are in different places, they cannot talk to each other. And the square matrix is like that. And then they are asked to do certain things. So Van Neumann says, oh, take a square. And Van Neumann calculates the square. You see, the color is the same. But you see, the color of the matrix of Hilbert is different. So I don't tell you what the semantics is of the color, but it means they are different in this case, okay? Okay, then Hilbert says, bullshit, I cannot calculate the square of that matrix. And he's not stupid, so he's right. So what's going on? And then says, I calculate the inverse. Okay, then Van Neumann calculates the inverse, and then Hilbert calculates the inverse, but it changes color. So it became something different. So what's going on? And then transpose. Well, in this case, Van Neumann changed the color, and Hilbert doesn't change the color. Okay. And then eigenvalues. And eigenvalues says, Van Neumann says, sure, eigenvalues. That's what I do all the time when I do calculation and operate in quantum mechanics. We calculate the eigenvalues. And then Hilbert says, oh, then what a bullshit, I cannot calculate the eigenvalues. Determinant, same story. And you know that determinant and eigenvalues are connected, right? So this will also be not possible. And they say, can you change coordinate of that in a certain way? Yes, I change it like this. Oh yes, I change it like this. So what's going on? Well, I tell you. And then you exactly now don't see what you should see, so I need to do something about it. Yep. Yep. The point is that these are both matrices, but they represent different objects. The one on the left is a linear operator, so it maps an element in a vector space to an element to the same space. The one on the right is a quadratic form. A quadratic form, you can see it as a quadratic form, or you can see it as a linear map that maps a vector to a covector. Example, well, think about the inertia matrix, right? It maps a velocity to a momenta. A momenta, you know, Newton's equation is not F is ma, it's F is p dot. So force is a dual vector, so it's a covector, so p dot is a dual vector. So it meets the velocity, so precisely what's going on. So these are certain representations, not so important, but if you take the square, no problem, because you go from V to V, and again from V to V. Fine, so you can do that. But you cannot do that there, because if you go from V to V star, you cannot then use the map that goes from V to V star, because you are in V star. You can't, it makes no sense. The inverse, well, you can do the inverse. You can go from V to V, and the inverse goes to V to V. It's the same thing, right? Doesn't change. But if you go from V to V star, the inverse will go from V star to V, okay? So it's a different thing. So it changes the color. The transpose is what is called the adjoint map, which is used all the time. It's a transpose Jacobian, okay? So when you go from coordinate space, velocities, velocity in joints, to velocity in workspace, that's a map. Okay, that's actually called the push forward on the nonlinear kinematic map. And then you have the pull back, which goes backward, And it does not map velocities, map forces. It's the same thing. So you think that Jacobian transports are tensorially is the same thing, you just use it differently. And here you can do that. Also, you cannot talk about symmetry of a matrix if it's not a quadratic form, because if it's a quadratic form, the object it acts upon are the same, are two V's, quadratic form. You can talk about transpose and you can invert it. If it's a linear operator, you can't. It makes no sense. Eigenvalues, well, it's very easy. You cannot talk about eigenvalues of quadratic form. Why? Because that's the definition of an eigenvalue. Okay? Because if you have a map, you go from a vector space, you multiply it by a scalar, you are still in the same space. You just use the multiplication in a vector space. Okay? So you cannot talk about eigenvalue of a matrix. It's done all the time in our field. I could cite an enormous amount of papers. You cannot take eigenvalues of matrices, of inertia matrices. It makes no sense. And so on and so forth. I hope you got the point more or less. We could talk about it more. Okay, so what are wrong concepts as a consequence of this? Okay. In general cases, for example, manipulability, which is used all the time, if you get to SE3, to Lie groups and rigid body motion, is a wrong defined concept. Be careful about it. I don't have the time to go into it. If we have the break, I can answer if you have more questions about it. Just want to show you how important is geometry in this. Eigenvalues, I said, of matrix, an n quadratic form is wrong for the reason I gave. Unless you have another metric, not the same, another metric you can use to what it says, rise the index. That's the terminology which is used. Inertias have no eigenvalues. In general cases, stiffness is only defined at equilibrium, is not defined anywhere. There is very nice work of Milos Defran and Kumar, for example, on this in the past. If you consider symmetry of a matrix, you cannot calculate its trace, because the trace is something you can only calculate on linear operator. And symmetry, you can only talk about quadratic forms, as I show you. You see, there are a lot of things that it's important to know, etc., etc. Matrices are not mathematical objects. This has been known for ages. And yet engineers do not learn this most of the time, and sometimes not even mathematicians, okay? Because tensor calculus, which would take an hour to explain, it's just disregarded in education. It's terrible. And there are many mathematical fairy tales in engineering books of these reasons, you know. Just be very, very critical. And in that respect, I would like to say, learn this sentence. You know what that means? Nullius in verba is Latin, okay? It means don't take anybody's words of it, okay? I always tell my student, don't trust me. I should be able to explain you things. If I say something, don't take it for me just because I'm telling you that. And it's the same here. So attack me as much as you want. And this is actually what is written in the core of the oldest scientific society in the world. That's the motto, okay? Nullius in verba. What about Lie groups? This is obviously. And what is a group? Well, a group, as was said, anticipated, is actually a manifold, a differentiable manifold, okay? So it only is not a topological, it's really also, you can do calculus on it. And it has an operation, because a group has an operation. Okay? So what is a group? A group is an operation, so it's an algebra. You take two elements and it returns an element in the same set. So it's a pair, it's a set and an operation. That's what a group is. And it satisfies associativity. It has an element which is very special, it's called the identity. And it has, for each element in the group, you have another element which is called the inverse of that element. That is what it is. That's what a group is, okay? Examples, many, many. You can think of motions, abstract motion, matrices. There are a lot of algebra, all the things you use in real numbers and summation and multiplication have that structure. And then you can, if you have two groups, you can define what are called structure-preserving maps. A question, suppose you have the bare set, no structure of a group, okay, I have a bare set. What is the structure that a set has? Does anybody know? What can you say about a set in general? Not much, but what? You can say something about that. Sorry? Yes, and you can count them. Cardinality, okay? That's the only structure set has. So a structure-preserving map in sets is called a bijection because it doesn't change the number of elements. That's what a structure-preserving map is for sets. For groups, you have extra structure because you gave an operation, right? So what would then be the structure-preserving operation? This. It's obvious. You cannot be anything else, right? So if I hadn't written this sentence, you could have come up yourself. So what is a homomorphism? Is a structure-preserving map for a group, full stop. So what is the Lie group? Well, the Lie group is a manifold and a group, okay? It has these two things together. And it's unbelievable how these two things together, how powerful they are. Nature is based on this description. It's absolutely amazing because it will be able to describe symmetries of the universe. So let's try to picture how that looks like. So intuitively is a manifold, you know, and just graphically, I'm not as good as now in making pictures. I'm doing my best. So this is a manifold, okay? But this manifold has a very specific point. It's called the identity, okay? That's the one I indicated there. And for finite dimensional Lie groups, okay, there is a very famous theorem, it's called Ado's theorem, that tells you that there is always a matrix representation of that. But the Lie group is an abstract thing. You don't need to talk about matrices, okay? But most of the time we do, and that's fine because of this theorem for finite dimension. Then if you have, you know, it's a manifold who has tangent spaces all over the place, and also the identity, of course. So that is called the Lie algebra, as Naomi mentioned previously. The funny thing is that because it's differentiable, there is some magic going on, which I don't have the time to describe, that lets a certain operation appears, which is bilinear in this algebra. This is called the commutator in the algebra. You basically take two elements, use these vectors in that tangent space, and it returns a new one, okay? And it satisfies certain properties I don't have the time to go into. And we have, again, another thing, which is the exponential map, okay? But it's a different way of construction of the exponential map, okay? They can be related, but it's a different thing. Because what you do basically in this case, you use this symmetry that the groups gives, and you say, I have a certain velocity in this direction. How does this move along itself in some sense by preserving this, a kind of parallel transport, if you wish, which is actually parallel transport. An example, rotations. Okay, a rotation is SO3, so again, it's a Lie group, and we often call it orthonormal matrices. That is a representation of the group. That's not the group, it's a representation of the group, okay? And the I is the identity matrix, right? And then if we have a curve, basically something that rotates, okay? And then at a certain point, we have a certain value, a certain rotation, which is a rotational matrix. So we can take the time derivative of that rotation, okay? That's just the time derivative of all the points, and that's a vector. It looks like a matrix, but the matrix is a vector. Matrices are vectors, okay? So our dot would basically be belonging to that space. That's the geometry about this stuff, okay? But thanks to the fact that it's a Lie group, and by the way, I actually already was wrong because it's a rotation matrix is not the configuration. It's something that acts on configuration. I'll come to that later. Okay? So if you have this situation, then there is a way you can map that element there to the identity. There are actually two ways of doing that, but there are the two unique ways to do that. Okay? And that is where the omega lives. Okay? So while you use omega all the time, but now by looking at this picture you can learn two things. The omega is independent of the configuration. You don't need to talk about what R is. But you cannot integrate it because it's always attached there. You cannot integrate the vector that's not moving. You can integrate the vector if you follow where it's moving, okay, which is R dot. You can integrate R dot, you cannot integrate omega, okay? You can see that this bracket I told you is the vector product. Okay, then what you do, the vector product that, you know, it's given to you seemingly by God at school, it's actually this. That's what the vector product comes from, okay? And another thing is that you can generalize this to homogeneous matrices. That's a different group. It's called SE3 group. Okay. But then you see that what very often in robotics is used, like to talk what people normally call twist, let's say omega and R dot, you mix two things. The omega is there, the R dot is there of the translation. It's wrong. It's not geometrically consistent. Okay. There would be a lot of things to be said about it. I don't have the time to go into it, but at least you have a picture of this stuff. Now, what a Lie group is important for, because the Lie group has an action. A Lie group acts on things. So if I'm precise, if I have this body, this has a certain configuration. And if a Lie group has an element that rotates, if the thing is here, it rotates it like this. If the thing is here, it rotates it like that. So it acts on other things. That's what the group is important for. Okay, it's a very different thing. So it is very important, and we'll see why in the context, because if you give me a group element and a point on the manifold, this action will tell you how this group moves this point to new points in the manifold. Okay, and once you have that, you can take the time derivative. Okay, you can say the derivative. So you can take a curve through the identity of the group. Keep a point fixed. That will map a curve passing through certain points. And then you can make this map of a velocity representation in the algebra and the velocity representation in the points. You will see this clearly later. Are there any questions so far? Okay. Port-based physics. So now we have the basic math ideas. So about what we need to talk about port-based thinking. You know who this lady is? Very good. Emmy Noether. So she was described by Einstein and Hilbert as the most fundamental, being given the biggest contributor to mathematics of all women in history. Okay. At that time, and I still think is the case. Okay, if it was not for her, we would not have, Einstein would not have finished general relativity. We would not have a lot of things in algebra, and so on and so forth. She was a genius, and she never became professor just because she was a woman. Thanks God, things have changed. And Noether's theorem says, which is one of the things she did, which is very, very fundamental for physics. She basically says, I'm very simplifying here things, she says that if there exists a continuous symmetry, okay, then there must be a conserved quantity. That's basically, and the other way around. Okay, that's basically what Noether's theorem says. And this is the mathematical reason why their energy exists. You know, energy has not been discovered by Noether, of course, in history, but this is the reason why it exists. Because the fact that we have physical laws that are invariant in time, so we can call them laws because they don't change, okay, in time, is the reason why there exists a function which we call energy, which is not changing. That's it. I mean, it's as simple as that, okay? So energy is the physical invariance, physical laws invariance in time, okay? And this is the mathematical reasons why energy exists. Furthermore, Einstein, not one of the stupidest guys of the previous century, said that all physics theories will be very likely one day overthrown, except thermodynamics. I never liked thermodynamics when I was studying. It's the most fundamental part of physics you can imagine. Okay. So energy, the importance of energy is undoubtedly useful, okay, for robotics, because robots are physical systems. Okay. So we really need to describe a way of interaction, because interaction is exchange of energy. It is how you couple systems to each other. Okay. This is so fundamental. Okay. And we need this. We need to really use this. And in fact, citing a very famous mathematician and philosopher, Wittgenstein, he basically said, what we cannot speak about clearly, we must pass over in silence. And unfortunately, there are very few politicians, especially nowadays, that actually know about Wittgenstein, okay? But if we want to talk about interaction, we need to use the right mathematical tools. Otherwise, we just do mumbo jumbo, okay? So how are we going to do that? The decomposition in physics and pore-based. Let me try to be as simple as possible. If we have a physical system and we want to decompose, why do we want to decompose physical systems? That's what engineers do all the time. It was basically in the theory on reasons that the Cartan, the one that gave you the Cartesian frames, okay, it basically gave how to solve a conceptually big problem. You decompose it, you analyze the parts, and you recompose it. You do it all the time. So it is a very important toolbox for what we do as engineers, right? So if we have a total system and we know that energy is important, I think it should be obvious that when we decompose, we don't use block diagrams, mumbo jumbo, drawing the equation in blocks, but we keep the structure and the energy preservation, okay? So we want to split it in two. Of course, we will split in many things. I'm just doing the example with two, in such a way that then each of these parts has an energy content representation. And it should be in a way that the sum of the two energy is the same as the one I started off with. Otherwise, the decomposition broke up the conservation of energy, right? The question is, of course, how do you describe this interconnection now? If you want this to be the fact you want to follow, because energy is so important, right? Well, you know that if the energy is important, should be the same. You know that when energy goes down on one side, it goes up on the other side, right? It's what you have. So that it means that there is a common power flow, which is describing how this energy transfer from one side to the other, right? So if we have a way to describe that, which is general, independent of anything else that the pure mathematical structure we need in order to do that, then we have nailed it, right? And why is it going? Oh, I was touching the touchpad. Okay, so what we do is, and another thing we know in physics, by the way, is bidirectionality. If two systems interact, it's always a bidirectional exchange, action-reaction. This is the embodiment of Newton's third law, okay? Is action-reaction. So I don't know what these guys are mathematically. I just know that part 2 has an effect, causal effects on part 1, which I call E as a function of time, and the other one, the other way around. Oh, sorry, the other way around. But you see what I'm talking about. That's all I'm saying. Now, the question is, of course, what is this nature of these things, mathematical point of view? Because Poincaré told us that if we find that structure, we nailed it. We don't need to talk about other things. That's what we need to talk about it further. Okay, well, there is a very simple way of doing that, and that's called duality. So these two variables, you see, I don't add any other structure. I'm telling you, if one of these two things is belonging to a vector space, and the other thing is belonging to the stool of the vector space, okay, then once I naturally pair them, I don't metric nothing. I pair them as I told you. I get a real number. That real number I can use to represent the power flow at that instant of time. Boom, done. Okay. Well, this is very simple. It turns out that you can describe the whole universe with these concepts. I'm not exaggerating. I'm working with Friedrich Schuller. Some of you may know, is a phenomenal theoretical physicist and mathematician, has the best course in differential geometry on internet. And he's blown away about this, and now we are working very closely on this kind of stuff. So it's something which is not known, but it is the way that physics should be actually described. And in fact, this is very general, because, you know, if we talk about electrical circuits, this vector is just a current, for example, and the dual vector is a voltage. If we talk about multi-body dynamics, well, it turns out that you need to describe them with the Lie algebras, SE3 and SE3 star. But you can go to fluidodynamics, and this is what I did. You see, all these things on the right, which I'll just give you a glimpse at the end because it needs some more time, is precisely this, but the concept is the same. Okay, it's just that this vector space on the right side is infinite dimensional, so what the heck, okay? And so we can write it like this, and this is the notation that is used in bond graphs, for example. We just have one bond, and if this pairing of these two variables is positive, it means in this case the power goes from 1 to 2. And if it's negative, it goes from 2 to 1. That's it. This is properly defined for any possible imaginable vector space. I only use duality. I don't need any extra structure. And any field in physics, this works. Okay. And in fact, I'm working now with Frederick on quantum mechanics. So this is not only for classical physics. This is even more general than that. So this is about how you interconnect things, but how you describe these things. Well, you have these two, you can use ODEs or you can use PDEs, okay? But I will only consider ODEs. So this is the mapping you have. So energy is not a function of time. No, it's a function of the state of a system, okay? Energy is a function of a state, and the state is a function of time, okay? There is this composition in what's going on. But what is F and what is H? How should I describe it? Well, you know that the less structure you give to something, the less you can say, right? So we will give structure to that, and you'll see why, in order to preserve this property. So it turns out that you can take these equations, which I indicated here, of this sign, in this form, okay, just take dH is a partial derivative of the energy with respect to the state, because that's what the function of it, okay? This is a matrix, this is a transpose of that matrix, which is the adjoint, so what I said before, the pullback. And J is a skew-symmetric matrix. Can you talk about it? Yes, because it's a quadratic form. I can invert the indices, and if the sign changes, it's skew-symmetric. And R is also a skew-symmetric matrix, because it's also a matrix which has is a quadratic form on the dual way. So you see, you can talk about these things. So, but why is that important? Why is that structure useful? Well, this is the reason. If you take H dot, it's partial derivative of H with respect to X times X dot. Okay? Well, that is the natural pairing about H and X dot. dH is not the gradient, it's a one form. It's called a one form. It's dual to velocities. I don't need any extra structure, any matrix in order to talk about the change of H. I just pair the differential of H, which belongs to the dual, which is Tx star, you'll see it later, and I can do that. But now, so this is where they belong to, and now if I substitute the dynamics equation I gave you, this pops up. Well, the first one is quadratic in J. J is skew-symmetric, so this is equal to 0. Power conservation. This is positive definite, power dissipation. And this is the power supply. Why? Because if you use the second equation, the outputs equation, which is related to the first, that's what you get. Bam, you have energy balancing implied to that. You can further decompose it, and you can further decompose it, and you get this. And what you get here is you see that I decompose the old structure in pairing, okay, which you have here, the power coming here and the power going here is the same, so that if I take the pairing of this and this is equal to the pairing of this and this, because this is the adjoint of that. That's the way you define it, okay? This is just energy distribution, this is energy dissipation, and this is the storage. Guys, at what time did I start? Because I started much later than 12. 12:15, okay. So you see, this is the structure to decompose about port within the system itself as well. But can you notice something very important here? Look, what is this guy doing? You see, here is vector space are defining depending on the configuration of the state X. Here they are not. What geometry do we need in order to describe that? A Lie group. Okay, so what it turns out, and actually this is something that people do not realize, you cannot even write the equation x dot is equal to f of x and u. It makes no sense. You can only talk about what are called affine systems. X dot is equal to f of x plus g of x of u. And g of x is the action of a Lie group on the state. So what it does, why this is important, because then the vector space, which is independent of the interconnection, and why is this important? Why do you need something which is independent of the state on the port? Well, it's very easy. Because if you talk about interconnection, the system on the left has a state and the system on the right has a different state. You need an Esperanto, you need a way to talk both at the same time. And you cannot do it otherwise than having a Lie group, a Lie algebra, I should say. There is no other way. Okay? So you really need this. Why? Because what this does, it acts. So you see, if I have now a velocity which is in the bond, so on outside the system, it really, that this is representing the whole vector field everywhere. Depends, you tell me where you are, I'll tell you what vector velocities you have or change of state. Okay, this is really the geometry that you have. So physical decomposition, okay, and is described by what's called an energy port, which is V cross V star. It's just the pairing. It's together, you take them together. That defines a port, okay? And you need a Lie algebra. So there needs to be a Lie algebra in order to talk about interconnection. Can you generalize those things to the distributed system and to the bird? Yes, you can. The way you do it is just a bit more of math. Because power, when you talk about, you need to use what is called exterior calculus. And the idea is like this. So power is then a density. Because if you have the wing of the bird and you want to describe the power that is exchanged between the fluidodynamics domain and the elasticity of the wing, you integrate a power density on the wing. Okay, so the total power transfer is the integral of a density. And if you have a way, and we do, to decompose this in a natural pairing, okay, which is indicated with a wedge or a wedge dot, which is something else, but really related, is a mathematical pairing which is natural, which is related to Poincaré duality, by the way, then you're done. So, and this is all what exterior calculus gives you. It is unbelievable we still do integration in the way we do without knowing what differential forms are, because this is what this guy did, and there are millions of reasons why you should do it different that is taught all over the place. Okay? So by doing that, we studied Euler equation, for example. These are publications, so in a very fundamental way, to n dimensions. So we can also get to whatever dimension you want. We talk about advection about it. We talk about Navier-Stokes, Fourier-Navier-Stokes with turbulent generation and entropy generation. And thanks to this, to moving boundary, because you have two PDEs that are interconnected, and the boundary, the surface of the wing, is moving all the time. How the hell do you do that? It's more complicated than that. Two PDEs that are interconnected with varying boundary, and the boundary is moving. We can do that. And then, thanks to this mathematical structure, we have integration methods which are structure preserving. They are outperforming anything out there that you can imagine. ANSYS is out of business if this stuff is properly implemented. Okay, and there is a library, the open source library, you can look at if you're interested. And this is something about nonlinear elasticity we've published, which I think I'm very proud of. I don't have the time to talk about control. There should be, I could show you how control is basically, you can use as effectively control and solve many of the problems that people still think that they exist, that don't exist as long as I'm concerned. And let me go to the conclusion. So, just playing a game, and then I'm in conclusion. Because this is a bit of a paradigm shift, right? You know what this is? This is called a dovetail. You have two objects relative motion, 6 degrees of freedom. We know that where robotics is, right? So, and this is used all the time because this system fixes basically 5 degrees of freedom and leaves one open. Okay, this is this one. Then once we assemble things, we connect this, we put a screw down, and then you fix the 6, and we assemble our IKEA stuff. Okay. Now the question is, do these two things move with respect to each other? Who's for yes? Who is for no? The no wins. Unfortunately, that's not the case. Okay? You see what's going on now? Oh, so are there other motion? Of course, there is a symmetry here, discrete symmetry, right? We could take the other diagonal. Suppose we get that out. Are there more? Who's for yes? Who's for no? The yes wins. They are infinite ones. So what's going on here? You see, you are drawing conclusions to what is going on just by looking at the outside. So your critical attitude, academic critical attitude, is not good enough. Okay? I'm playing the teacher, I'm joking, but you see, but you tend to do it very fast to get to this conclusion. Always ask yourself, what do you see? Because what you only see is on the surface. You don't see what is behind, so you can't say anything about what is behind, right? Okay? So you should see if there is an implication that brings you to the structure which is behind. So break out your partner, thinks about out of the box, and I hope that with this lecture I did give you some things to look at. So let me draw to my conclusion. I gave you an introduction to pore-based way of thinking. I guarantee you that this is really mind-blowing. When I started working this stuff, because I just came across bond graphs, I didn't get the point. I said, well, why do people waste time writing things like that? This changed my life professionally, I guarantee you. You have no idea how powerful that way of thinking, which has been mathematically evolving, is. Okay. Physical interaction is right about that, and in fact, this works also for quantum mechanics. Okay. So paradigm shifts, do not be blinded by what you think, because I think that, and this is my motto, epistemological growth is not about solving a problem, as a lot of people doing learning are doing. There's just a bunch of data and learning, okay, but understanding why the problem is solved. Okay, so I'm not undermining the extreme value of learning. Don't misunderstand me. But you should understand why things work. Thank you very much for your attention.